Noodle, okay.
Use Moodle and they put a timer. There's a time frame to take the exam, and then within that time frame, there's a timer. So for example, it's like you have a 2-hour time frame, but the exam is only an hour and a half, and within these 2 hours, we have to do it.
You see, the good thing by the end of this, finishing your school, you become an expert in noodles, call, and all this technique.
I don't think that's something we can put on our CV.
Why not? You have some experience. Your experience is more than me because I have no idea what is going on here.
Maybe Zoom to be able to work at home and use Zoom.
No, I don't know. I mean, it's nobody knows these days. Therefore, they're trying every different technique. Everybody comes with his own or her own way of doing it. And I believe the easiest way here is to give a take-home exam, open-ended question, and let them work for 2 days and give it back to you. Therefore, that's the way everybody's safe.
For your midterm, what's the format looking like? Is it multiple answer question, or is it development question with calculations?
My exam is always easy. I gave you a choice. You come up with 4 questions and with 4 solutions. Is it good?
So I decide the question. I don't like you.
I'm trying to write the exam. I believe it's at the level of your assignment, the same level of question. Give you 2 or 3 questions. Again, we remember his midterm is you have only 1 hour and 5-10 minutes. Therefore, something that you can finish it in 40-45 minutes. At least you can go back and verify the answer.
Sorry, go ahead.
So are you gonna take the calculation we make on a piece of paper, or you're not gonna take those?
I believe that is more fair to you if I take the calculation.
Okay, so we're gonna be asked to upload the PDF, because this is fine by me. It's just I prefer this way because it's harder to make the calculation on the computer.
No, it's also more fair, because if you make a mistake in calculation and your answer is wrong, that we don't get any credit. But it's better to give you to provide the solution. At least we can see what approach to use. And in case if you made any mistake in calculation, the calculator and that part, at least you don't lose the mark.
That sounds fair.
So, Prof, we don't need to write the procedure on the computer because this would be so long. So you say we write the equations and the procedure on the paper and just the answer on the computer?
To be honest, at this moment, I have no idea how the call is working, okay? But I need the calculation. I'm going to ask them, I need that you write the solution on the paper or on the computer and give it to me. I do not know call. Have you used the call before?
No, never.
Okay. I believe the one I send you an email last week or the week before, that just to go to approach. I believe, again, I never work with it and I do not like it. I don't want to learn anything about it. I believe they're asking you to write on your paper and then upload your solution. Okay. Let me see who is knocking my door. Anyway, I'm back.
Good afternoon, sir.
Good afternoon there.
I just joined the class.
Good. This is your first class?
No. Did I miss something? You talked about exam. We should write something. Or...
There was some discussion. Some students were complaining the question was too difficult. I said, we haven't had the exam yet. I don't know what they were talking about.
I heard that we have to write down on paper the procedures were.
They will send you some information.
Okay.
I believe you have already been approached, I believe, based on my understanding, that you can go on site and visit the call to see how it's work. I believe they send you some email. And I asked them, I need the solution. Therefore, I believe, again, this is through the email, usually takes 3 days to get feedback. I asked them that you have to provide your solution. Therefore, you should have the paper, you should write your solution, and I believe you have to upload your solution.
Okay.
Again, please read your email. The email comes from University IT, and they're telling you should go there, visit the website, and familiarize yourself with the technique, okay?
Okay, thank you.
I believe they have already sent it to all of you. Am I correct, or I'm just...
Not yet.
I didn't receive
I
anything.
didn't get anything.
Okay. Anyway, I will ask them to contact all of you because my understanding, based on the email, the way I read it, that the student will be contacted. That was 3 days ago. I do not know, probably today or tomorrow or the next week they're going to contact you. They will ask you to go and visit the website and familiarize yourself with the ECHO goal. And I believe also they give you some way to practice it. Again, don't ask me because I'm not the expert in that area. I'm sorry, sir, madam. Anyway, we will be in contact and I will make sure that you get the information, the latest this week. Any other question? Okay, let me start. I believe you see
I have a question, sir.
Yes, dear.
About the formulas,
Yes.
you said you would provide them.
Absolutely, I said nothing such a thing. I mentioned if it's in the form of the table or graph, I will provide you. If it's an equation just in the text, you should have it provided in 2 pages that you have. For example, if you look at here, let's just show you here. I'm giving you an example. This is not the part of the lecture. For example, if it's like this, here like this, I will provide you, okay? If it's given in the form of the table, I will provide you. For the rest of the equation that is in the text, you should, if you would like, you should bring 2 pages and have all those equations.
Okay, so we're allowed to have 2 pages of our own notes.
That's correct. That's correct.
Okay.
All the equation that you think is necessary, you can bring it along.
Okay, thank you.
No problem. Okay, we mentioned we were talking about boundary condition. We mentioned that, again, this is an overview that we have flow inside the pipe. And let me show how far we went. We calculated, we mentioned when is the constant temperature. We were able to calculate and we find, oh, I went too far. Okay, in the case of flow inside the pipe, and the temperature profile that we did that, we wrote an equation and we solved this equation based on the bond velocity, and we were able to find the heat transfer coefficient is equal to 3.6. Therefore, if you have a laminar flow inside the tube, if you have constant heat flux, it means that we are providing uniform energy throughout the pipe. In that case, does not mean the temperature is constant. The temperature of the surface is changing linearly, okay? In this scenario, the heat transfer coefficient is irrelevant, independent of the Prandtl number. Is it fluid, gas? Always the heat transfer coefficient, the Nusselt number is constant, okay? That's we followed. And the next one, when we had constant surface temperature, again, the temperature is constant. It does not mean the heat flux is constant, okay? In this case, the Nusselt number is equal to 3.4. Again, this is independent of the Prandtl number. Could be fluid, could be gas. As long as it's laminar, the surface constant, this is the Nusselt number that we have, okay? And we mentioned for the case we have, these are for the tube. It means when we calculate the Reynolds number, when we calculate the Nusselt number, we use D as a characteristic length, okay? When it's not circular, we have a table that provides you the value. But in this case, we come up and we define a characteristic length. We call it hydraulic diameter. In this case, hydraulic diameter is defined 4 times of cross-section area divided by the perimeter, okay? Therefore, we define something called hydraulic diameter that we can apply to non-circular scenario. If you look at here, when we are dealing with tube, here, this is Nusselt number, and this is for constant temperature, constant heat flux, and that's the value that we have, this number that we have, okay? The last one is friction factor. When we're dealing with non-circular like this, we have a rectangular system. This is A, this is B, and therefore, depending on the ratio A over B, the value of Nusselt number will change for constant temperature and so on. When I'm trying to calculate the Reynolds number, again, we use the hydraulic diameter into the calculation. Here, the diameter, the characteristic length, here is the characteristic length is hydraulic diameter. Therefore, now we have a table that will provide you the value of Nusselt number and so on, okay? Again, all of them we assume is developed. It means the velocity profile does not change, okay? Therefore, all of this scenario, remember here, for fully developed laminar flow. It means, what that means, it means the velocity profile will not change anymore. The velocity profile will remain. We have a temperature profile, we have a velocity profile, but both of them remain constant. They are not changing as move through the pipe. They are function of only R, they are not function of X, okay? X, the length. In this case, we are developing laminar here. It means the velocity profile has not been developed, it's still is in process. Therefore, we have a constant surface temperature. The average Nusselt number is here in the entrance region. From the X equals 0 until to the X equal XL when reach fully developed, we can use this correlation to calculate. Look at here, this is the diameter, and this is the length, the pipe, okay? This is in entrance region. When the difference between surface and fluid temperature is large, therefore we are using this one for laminar flow. All the properties, again, please pay attention. We have the equation, we can use them, but we have to make sure to use them correctly. Therefore, we have to calculate all the property, Prandtl number, and this, and the bulk temperature, okay? And the bulk, mean bulk temperature, okay? That's the boundary. And this is mu s, as I mentioned, this is creating a correction factor, because sometimes the temperature variation is so high that the velocity profile, as you know, that as the temperature will increase dramatically, the viscosity will be less for fluid. Look at honey, okay? Therefore, they're trying to look at this effect on the velocity profile. The Nusselt number for the entrance and between the fluid is that number, okay? This one. These are for this. This is when we have between 2 plates. When we have between 2 plates, again, we assume the rectangular system that follows this procedure. Therefore, now these are only give you an example, a sample of the type of expression you should expect. Again, these are for entrance, for all of them for entrance. That means still the velocity profile or temperature profile has not been fully developed. Again, we have to pay attention what temperature we calculate this physical property and what range of Reynolds number this applied. If you look at here, again, just trying to visualize it, visualization. This is, we are talking about entrance phenomena here, this one, right here, from here to here. This is expression they use, and look at here, after that, when it's fully developed, and after fully developed, the Nusselt number remain constant. Because the velocity profile will not change, the temperature profile will not change, therefore your heat transfer coefficient will remain constant, okay? And this is the entrance part, there is variation along the length of the pipe, okay? When we're dealing with the turbulent again, then as I mentioned, the textbook here also, they use both phenomena of fluid mechanics and heat transfer. They give you also some correlation that they calculate the friction factor, as you mentioned, about both of them the same, almost behavior. You know, I'm focusing here mainly on the heat transfer part. For if you have this correlation that mentioned, this is, we can calculate Nusselt number. As you can see, when it comes to turbulent flow, also friction factor is affecting because it creates more mixing, therefore will affect the heat transfer coefficient, okay? And again, we have another correlation that we have here, but this is more accurate only in this range. If it's Prandtl number in this range, and here is this range. Again, this is for this range that they are specifying, okay? Therefore, as I mentioned, most of them has been done experimentally, and they did the experiment and they're trying to plot and put the best curve on that range. For example, this is best curve in this range, and this is in this range, okay? And here we have another correlation that gave you. Here again is similar, but here the power is n. The power is n depend on the heating or cooling. Because if it's heating, n is equal 0.4. Again, this is the similar that we had before, that Nusselt number that we're correcting here, but rather than making correction based on the viscosity, they make the correction based on the Prandtl number. When it's heating, the Prandtl number is 4. When it's cooling, the Prandtl number is 0.3, okay? Therefore, please pay attention to all of this correlation, more or less good, but you have to make sure that you're using them correctly. When the variation in the property is large due to large temperature difference, then this equation will end up to become like this. Yes. Now trying to make this correction. Again, this correction mainly trying to correct for the velocity profile. Again, when the temperature is too high, the difference, the temperature surface, the velocity close to fluid close to the surface become harder, therefore the viscosity for fluid decreases, and therefore the velocity profile will change, okay? Again, they're mentioning all of them has to be about the bulk temperature here. Again, we have to see, and this one at the surface temperature. Again, these are only given sample equation that you have. If you go from one heat transfer textbook to another one, you will see another set of equation. But if you're dealing with the design a project, and you have to be very careful, you have to go to the library and look at handbook of heat transfer to give you more accurate one for your own application. Again, turbulent flow for this, again, another, you have this one, this was the first one here, and this gave you the second one. They get more accurate for the given range that they're providing between this range. Again, this another set of correlation. As you can see now, when we come turbulent, also including the effect of the friction, because this is creating, if there is roughness is too high, probably will create also more mixing of phenomena. For when we're dealing with liquid metal, again, it's like a mercury, and for the constant temperature and constant heat flux, you have another step correlation, okay? Again, you have to be careful, this equation is correct only this range applying to this part, okay? The relation was not very sensitive to thermal condition at the two surface and can be used for both of them, okay? Now, let's go back and see what we learned. Therefore, what we covered here in chapter 8, we gave you a set of correlation that you can calculate the heat transfer between fluid inside the pipe. This is only inside it, and also for both laminar and turbulent, okay? Therefore, this is the part we have already covered. Let's look at your textbook. If you have your textbook, you don't have to write it down. This is problem 67. Mention air, again, air at 20 degrees, enter a 5 millimeter diameter pipe, the length is 10 centimeter, with the average velocity of 5 meters per second. The tube was to maintain at a constant surface temperature. Okay, therefore now we have to make sure if it's laminar or turbulent, and therefore we have to use appropriate Nusselt number for that one. And the temperature of the plate is 100, the surface of the tube is 160 degrees. We would like to calculate the heat transfer coefficient. And later on, we're trying to calculate what is the temperature when it leaves the tube. Okay? Therefore, in all of the scenario, we have to do first, make a certain assumption if we need it, and then to find out what type of flow that we have, if it's turbulent or if it's laminar. And based on that one, we look at also the Prandtl number, trying to find appropriate equation that we can use to calculate the Nusselt number. After the Nusselt number, we go and calculate the heat transfer. Therefore, the first thing we have to do now, we have to go and find out the physical property of the air. Okay, mentioned coming at 20 degrees. And we know the temperature of the surface is 160 degrees. We have to start somewhere. Please spend a few minutes. Challenge yourself, please. And for the, I believe, if my memory allows me, I believe the physical property of the air you can find at table A15 at the end of your textbook. But the temperature coming here is 20 degrees. And if I remember correctly, if you would like to use the equation, we have to calculate all those physical variable parameters at the bulk temperature. And the bulk temperature, I believe, it means T in plus T out. I do not know what is T out. Therefore, the first thing I have to make an assumption. Said louder, please. I'm sorry.
I don't think he's trying to speak.
Okay, he's talking with his friend. That's okay.
Is it reasonable to assume a temperature of, I don't know, like 80 degrees?
Any number is correct. But again, if I'm looking at that part again, is the temperature is 160 degrees. Hello, could you please turn off your microphone, please? Gentlemen.
You can mute all the microphone as a whole, so you can do that.
Again, this is a bunch of bozos. They were trying to be smart as fuck. Could you please turn off your system, sir? Don't joke with me. I'm a nasty person. Okay, let's start to do that. Okay, therefore, the first thing we have to do, we have to look at also look at the physics of the problem. The pipe is 10 centimeter and it comes with 5 meters per second. And the question here is, what you think could be sort of appropriate number for that exit temperature? Again, it's only 10 centimeter. We can make assumptions 80 degree. We can make assumption 100 degree. But any number, we have to come back and verify it. Okay? Therefore, make an assumption. And make an assumption to see what we can do it. Okay? Therefore, that's, we have to look at this 10 centimeter. And that's we're trying to figure out. Okay? That's the way to do that. Therefore, we make a study exit operation, properties constant. Again, these are something we are trying to make simplify for ourselves to be able to use the existing information that we have. Again, these are the information that we can use. Again, we assume the air property at 50 degrees. It means if it's coming at 20 degrees and we assume it leaves around 80 degrees, as you mentioned correctly, therefore the average property becomes 50 degrees. That's acceptable. But again, we have to come back and verify at the end, okay? And for this, we are calculating all the physical properties at 50 degrees, okay? Again, this is an assumption. We can make 100 degrees. We can come back and verify. Therefore, if you look at this table and we look at this physical property, okay? And now we have to go back and say, okay, now I know the physical property. I calculate the bulk temperature because this is what we have been asked to do that. And the textbook mentioned bulk, 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 bulk. Therefore, that's we do that. And again, since we are in table number 15, we also calculate physical property of this one to see if we need it later on or not, okay? Probably we do not need it, probably need it, okay? Therefore, we calculate all those parameters, okay? Now, the next step, here I'm going to calculate my Reynolds number. Could you calculate the Reynolds number?
Sir?
Yes, sir.
Why do we have two viscosity?
Again, this is something that we, as I mentioned, at this moment, since I'm over there, if I remember the textbook, I have to calculate some of the equation needs a correction based on viscosity at the surface temperature. Therefore,
Okay.
this viscosity at the bulk temperature, this viscosity at the surface
Okay.
temperature.
All right.
And probably I have to also calculate the Prandtl number at surface temperature, because if I remember the equation I had, some of them the correction was based on viscosity, some of them the correction was based on the Prandtl number. Just I wrote it here, okay? Now, therefore now we'll go back and calculate Reynolds number. Therefore we have this tube, we know the diameter, we have all the information, and my Reynolds number mentioned 1,390 decimal. Therefore that indicates I'm in laminar. But still I have to verify one more assumption. This is the other assumption, gentlemen, ladies and gentlemen.
The temperature?
No, because this is not laminar. As I mentioned, the tube is only 10 centimeter.
Oh, okay.
I have to calculate, is it fully developed or not? Because we mentioned probably, if you remember, let me go back. Here we have for laminar flow that we mentioned based on this one is constant temperature. Now we have laminar flow, therefore this is my value. If I assume it's fully developed. If I assume it's fully developed. If it's not, therefore I have to go back and to get entrance phenomenon. Okay. Therefore, how do I know how much is the entrance length? Do you remember entrance length? Therefore, if it's small, I can assume it's fully developed, okay? Therefore, we have to go back and let's look at this part. I can look at for laminar flow. This is this one. Remember, we had the expression to calculate entrance region for velocity and entrance region for the temperature. Do you remember these two equations, or you would like to show it to you? For velocity, it was 0.05 Reynolds number times diameter. If I put this Reynolds number here, if I put the diameter here, it takes 34.8 centimeters to become fully developed. Therefore, that indicates the velocity profile is not fully developed. for velocity. I can verify also for the temperature. Again, this equation that we have for the temperature, and shows me that it takes 25 centimeter. Okay, therefore here they tell me the length of the pipe needed, the velocity become fully developed.
Sorry?
Here, yes, dear.
Does that mean that our temperature is wrong and we have to revise?
No, it has nothing to do with the temperature. This is only which correlation should I use? Which correlation should I use to calculate my Nusselt number? If it was a 1 meter pipe, 10 meter pipe, I said, well, look, forget about it. This is 34 centimeter and that's 10 meter. My velocity is fully developed, okay? But now I have only 10 centimeter. By the time fluid leaves the pipe, the velocity has not been fully developed. Therefore, it still is developing flow, okay? Therefore, I have to go back and use those. Yes, dear.
So here you use the Reynolds number for the average temperature.
This assumption I make, that's correct.
But the Prandtl number you used for the 160 degree or
160 degree, no, sir. This is, look at here, in all of the correlation we developed from the beginning, they mentioned we calculate the Prandtl number and Reynolds number in bulk temperature. The bulk temperature, it means the average temperature inlet and outlet.
The Prandtl number used here is the bulk temperature, not the 160?
This one, the one I used it here is the bulk temperature, sir.
Okay, but we didn't get that from the table.
No, this equation, sir, let me go back and just show it to you. This equation was at the early part of the lecture we will provide you. This is the equation here is the entrance part, the thermal entrance. We mentioned for laminar is this equation. This is for okay.
Okay, thank you.
This was we mentioned the fluid that we have here. If you remember here, sir, we mentioned this is the tube I have. It takes a certain length of the pipe. The velocity becomes fully developed. It takes from x equals 0 until this x, the velocity becomes fully developed. After that is already fully developed. Here in this region from x equals 0 to x equals LT, the temperature profile is developing. From x equals 0 to L equals H, the velocity profile is developing. Okay, therefore here we call it developing part, entrance part, okay? And these are the equations that we find we have for this one.
Okay, I'm just only confused because when
no, that's okay. That's okay. That's the whole idea of the discussion. No problem.
Because when you got the numbers from the table, for the table E15, you got the Prandtl number for the surface temperature, not for the bulk number. That's why I'm confused.
I believe that Prandtl number, if I let me go back to my, because the Prandtl number is, I believe, is for bulk temperature. Again, sir, let me, where is my slide right here, right here. Here.
Yes, here. This number
is at this Prandtl number, I believe, is at also at bulk temperature. For the air, the Prandtl number does not change dramatically.
Okay.
Okay.
Thank you.
That's 0.71, 0.72. That does not change dramatically. But the TS viscosity here, this part, this part. Okay. Okay. Therefore, now we find out what is the this one that indicate the velocity profile and temperature profile has not been fully developed. Okay. Therefore, now I have to go back and trying to use those equation that is given for thermal entrance. Okay.
Sir?
Yes, sir.
So all the results that we have right now indicates that we should consider the flow to be turbulent.
No. The flow is laminar. The flow is laminar, but is not fully developed.
Okay.
Okay. It means velocity enter the pipe is uniform, and it slowly move to become parabolic. The shape has not been completely constant.
Okay. And
Okay.
there's a formula for transition region.
Yeah, this is at this
or development region.
We are not talking about transition region. We are not talking about transition region. We are in the laminar flow, but it is still not fully developed. Let me go back and again start to show you that the slides are. Yeah, we mentioned right here. Right here, okay? Look at this part, the fluid comes here, we assume it's a constant velocity, okay? And then slowly is the velocity become changing. Here is flat, and here is slowly become like this, and as move here, become like this, and finally become here. This is, we call it fully developed. It means after this part, its velocity profile will not change. If the fluid was laminar here, remember, my friend, we calculate the Reynolds number based on average velocity. Average velocity here is the same as here, the same as here, the same as here, the same as here. And inside the pipe, if the flow is laminar, will remain laminar for the rest of its length of the pipe, will not change. Okay, therefore that's the difference between the pipe and flat plate. For flat plate, as the length change, the velocity will change. But inside the pipe, if it starts laminar, remain laminar. That's one thing between laminar and turbulent. The other point that we're discussing now is about the entrance phenomena. At the beginning, we assumed the velocity is uniform. Look at here is uniform. And as move along the pipe, the velocity profile is slowly will develop. Okay? And then finally become fully developed. It must become parabolic here. After this point, the velocity profile will not change. What that means profile? Here it means if at this place, the velocity was 4 meters per second, it is 4 meters per second, okay? It's remain 4 meters per second. But here it was 3.8, but now it's become, because here is developing, and here is developed. Therefore, here, yes, yeah. Hello?
I said, okay. I understand.
Therefore, this is very important to understand the physics of understand. Okay, this is no problem. This question asked because that's the whole idea. We make sure that we really understand the physics of the problem. Okay, and now we mentioned for this here, we have equation. The length for laminar flow. For laminar flow, is that much. For velocity, for temperature. Therefore, if fluid enter the pipe is laminar, end of the pipe is laminar, will not change. Okay, and if it's turbulent, and that's the way we calculate. Okay, therefore now we have to go and look at here. Therefore, the flow is laminar because the Reynolds number is less than 2,300. But hydraulically, that means velocity and temperature is developing now. It means the profile is changing along the pipe. Therefore, we go and use the equation that was mentioned for that case. In this case, if you remember right here, that's why we wrote, look at here, because this equation for laminar, but for entrance portion, we use this equation. Therefore, this is, we have the Prandtl number, we have Reynolds number, we have length and diameter, we put it here, and these are the physical properties that we're making the correction for the velocity profile. Therefore, from here, we find the Nusselt number is 6.6. What that means, again, I would like you to understand the physics here is, it means the convection phenomena is almost 6.6 times bigger than conduction. Okay, therefore that's the meaning of Nusselt number. Therefore now we calculate the heat transfer coefficient here. It comes 3.36.5. Okay, 36.5. And then they were asking us one more question. The question was asking what is the mean temperature leaves the pipe, the average temperature. Okay. Again, remember we had this set of equation that we developed for the case of constant temperature, if you remember, and we are going to do that. That was a mean log temperature. Okay. Therefore, we are trying to use this equation. This equation gave you the exit temperature. This is the mean exit temperature. It means the average temperature at the exit. Okay. The temperature is a function of the R, but this is the average temperature of that one. And that the correlation that we need the value of H that we have defined here. The surface area, again, these are the surface area. Mass flow rate of going to air, we have the velocity. This is cross-section area. This times this gave you volumetric, multiplied by density, give you the mass flow rate. Therefore, this is the mass flow rate that you have. Therefore, this is temperature 160, mentioned the surface temperature 160. TI, we know 20, therefore, this gave us 77.9. Now, therefore, we can see now that assumption was correct because we assume it's 80 degrees. That's what my friend mentioned. Now, 77 or 88 does not that much difference. Therefore, we are safe. Okay. Any question, please?
If like I said, we used 80 degree, what kind of results will we get at
Let's assume
beginning?
Let's assume you made a mistake.
Yes.
The temperature is 160 degrees, right?
Okay.
Okay, you assume 160 degrees. Therefore, 20 plus 160 become 180, right? Therefore, you're going to calculate all of your physical property at 90 degrees. And running the same procedure all the way to here. And you were finding that, oh, the temperature is not 90 degrees. No, it's not 160 degrees. Then you have to go back again to do all the calculation. Probably after 2 or 3 try, you will converge to the temperature you needed.
Okay.
Okay. I would sorry, my apology, because I was told there are sometimes that some people enter and give you some problem for our Zoom meeting. That was, I thought, one of those one. Again, my apology. Okay, therefore, here is we find a way. Therefore, please attention, understand what is fully developed, developing, what is the entrance region means, and when are using any correlation. Again, please pay attention to the limitation. It's not just using the correlation. You have to pay attention to correlation. Okay, here I use this value because entrance, because satisfy all the conditions that we needed before. But if you don't remember here, sorry. Going fast that direction, come back to this. What is going on here? Yeah. Okay, entrance region here. We use this correlation here. Okay. Therefore, here you can see all the properties evaluated bulk mean temperature except μs. Okay. Therefore, here it mentioned this is the one we have equation correlation to. Okay. Therefore, make sure there is no restriction here based for Prandtl number, Reynolds number, and so on. Okay. But mention this is for lamina. Okay. Therefore, that's this one. Well, if you are going to use this correlation here, therefore you have to also consider this one. But this is for flat, 2 parallel plate. Okay. Anyway, any question, please? Please ask any question you may have. Any question? Okay, now let's go back and let's go continue. Look at this problem. This is a textbook that you may have. Problem 121. Geothermal stream at 165 condensed. What that means here is, what information that gives you?
Change of state.
Pardon me?
Change of state.
The slowest.
Change of state.
Yeah, phase change. That's correct. What that means?
Phase change.
That's correct. What that means now? Okay, 165. Okay. On the shell side of the heat exchanger, over tube to which water flows. Therefore, we have tube. On the outside, we have some condensation, and condensation usually happens at a given temperature. Okay. Water enter for, this is that diameter of the pipe, 14 meter long at 20 degree. Therefore, the water temperature coming inside the pipe at 20 degree, rather than give you the velocity, give you the mass flow rate, 0.8 kilogram per second. What is the temperature leaves the tube? And how much of those steam condense? Okay, just spend a few minutes. Please read the problem. You may have the solution fine with me, but read the problem, understand, put your assumption, and put the steps that you have to follow, okay? Because that gives you some confidence that you really understand the problem and you're not going to the random solution, okay? We have mentioned every word has here has a string that you have. Condense. You have it.
Temperature?
Say it again, please.
Constant surface temperature?
Yes, sir.
That's a condensed mean, yeah?
Yeah. Therefore, here now is a phase change that you have here. Therefore, the constant temperature and the flow is coming here, the diameter given, the length of the pipe given is 14 meter long. The mass flow rate here have been given to you. Therefore, you have to calculate the Reynolds number, how you're going to calculate the Reynolds number. And now here you have to make a certain assumption. Please make those assumptions, put it in, and then here we're talking about the water. You go and look at the table A9, the physical property of water is given that, trying to do that. Okay, take a few minutes trying to do it. Please do it. That's give you some confidence, then you feel much better during the exam, please. Okay, let's move. Therefore, again, we have to make an assumption. This will help us to have a better understanding of the limitation of the problem here. We assume the velocity is a steady state. It means the temperature, everything remain constant, the velocity remain constant. And if you remember also in the problem, some of the correlation that I mentioned, if it is turbulent, probably in some equation that you need to know also a friction factor, okay? Therefore, we assume it's smooth, okay? At this moment, I do not know if it's turbulent, but again, assume that I know the solution. Again, the surface temperature of the pipe here, because we are measuring the condensation take place, there is a phase change. Therefore, from steam, it end up with the liquid. Therefore, the temperature remain constant under 65. And now you have to calculate something, okay? Therefore, here, the Mean temperature 85. What that means? What that means?
The exit temperature is higher than that.
Therefore, here we assume here is we are talking. Remember again, we have to be practical. We have to be practical. It's 14 meter long. Okay, 14 meter long. Therefore, it's coming here is at 20 degree in, and it has 14 meter long. Therefore, the temperature probably will be high. Okay, therefore you make an assumption. Okay, this is again, it has to be reasonable. Okay, anticipated around 85. Okay, therefore this is we're trying to calculate the physical property. Again, this is kinematic viscosity. This is your Prandtl number for water, and these are the rest that you have. Okay, and again, if you look at when you're on that table, because water, it mentioned, if you, again, that's why I mentioned, try to really first understand. Here mentioned what is the rate of the condensation, okay? It means how much the mass of the condensation. Rate of condensation, it means kilogram of steam per second. That's a concept. Therefore, if you put your solution from the beginning together and following this, that you see that you need that information that you needed. The energy needed when trying to change the phase from the steam to the water liquid, okay? This is the amount of energy that releases, okay? I'm sure, I hope you remember building science table 9.1, okay? Therefore, to put this number together.
Sir?
Yes, dear.
Is that what you're saying? You're talking about this because the PR number is 2.08 because we have a phase change?
No, pure, it has nothing to do with phase change. The pure.
Okay, so how is it 2 if consider 85 degrees?
No, PR is different thing, okay? I'm talking here is condensation take place. Condensation, what that means? It means is a process take place at a constant temperature. Right?
Yeah.
You agree?
Yeah.
Therefore, the transformation from steam to water take place at a constant temperature. That is
Yes.
okay. Now we come here and we have to make an assumption. Okay, you can assume your temperature living is around 80 degrees, 100 degrees, 160 degrees, what any number. Therefore, you have inlet temperature. You make an assumption what would be your exit temperature. T bulk, it is Ti plus Te divided by 2. But again, when you're making that assumption, a calculation, you have to also look at the practice of the sort of physics of the problem. And that we are talking about a 14 meter long tube. 14 meter long tube. Therefore, you expect the temperature of the water living at that point is be high. You can assume 60 degrees, you can assume is 90 degrees. Therefore, what assumption that you make, you calculate the bulk temperature. And that bulk temperature, you go and look at the physical property that you have. Okay? This 165 has nothing to do with exit temperature. This 165 is amount of the energy release when we change transformation from the steam to water. You get it?
Yes, sir.
Therefore, this is energy. This has nothing to do with Prandtl. All this physical property were calculated at mean temperature. At this moment, we do not know which equation that we are going to use. Therefore, we just calculated at the bulk temperature. If it's
sir?
Yes, sir.
I understand that. I was just on properties of air and not water. That's why I saw the PR number at 2.08 and was surprised. And then I went back to water and was like, oh yeah, we're dealing with water right now, so we have to change.
Very good. Let's move. Therefore, now we're going to calculate my Reynolds number. You can use this equation. You can calculate the velocity, average velocity, or you can, and then come to calculate Reynolds number. And I gave you originally also one equation that you can calculate directly from the mass. You have one equation that I gave you. It is 4 times mass flow rate divided by number, okay? That from there also you can calculate using mass flow rate, directly calculate Reynolds number. You don't need to come calculate the velocity and from the velocity come calculate here, okay? Do you remember that equation? Most probably not. Let me just show you again one more time because that will save you some time. This is the equation that we have here. You can use this equation, or this equation, 4 times mass flow rate divided by mu d. You know the mass flow rate already. You know the pi. You know the d, mu. Therefore, you can use this equation directly to calculate your Reynolds number. You don't need to come calculate the average velocity, okay? Okay?
Yes, sir.
Therefore, now we go back. Let me see where we were here. We were here. Therefore, you can come back here and calculate your velocity. Therefore, now we calculate anyway. We find that the Reynolds number is 76,000. That indicate the velocity throughout the pipe from an entrance all the way to the end is turbulent. Remember again, when we calculate Reynolds number, what is average velocity. Average velocity at the entrance is the same as average velocity at the end. Okay, therefore that's the case we have here. Now we have to go back to say this turbulent flow. What should I do next, ladies and gentlemen?
We have can get the Nusselt number using viscosity for that mean temperature.
This we can do that one, or we can also, if you want, like, I mean, 14 meters is long, but we can also verify if the entrance phenomenon, if it's fully developed or not, but this is 14 meter, that'd be fine. But if not, you can go back and look at if it's fully developed or not, which is greater than 10,000. And therefore we can look at here, we can measure 10 diameter, therefore it is 40 centimeter. After 40 centimeter, the velocity is fully developed. Therefore, we can assume it's already fully developed. No problem. Then we go back and we look at the equation that we have. The equation that we have, and we can look at it, which one is more appropriate for this phenomenon. The phenomenon here is the heating phenomenon that we are having. Water comes at 20 and leaves at certain temperature. Okay. Therefore, we can go back and use this equation. You can use this equation and trying to find out if it's okay or not. Okay. Therefore, this is one of the equations that we have. Mention 0.23, Reynolds number, Prandtl number, and so on. Okay. Therefore, this is one of the equations that we can use. We have some other equation, but here this is one of them that it satisfies the range that we needed. And we find the Nusselt number is around 248.7. Any question, please ask me if anything doubt is in your head, please. Therefore, we go there. Now we have Nusselt number. And the next step, we are going to calculate the heat transfer coefficient. And look at here, the heat transfer coefficient. This is the definition of the Nusselt number. We have Nusselt number equal this. We know D, we know K. The only thing is unknown is H. Therefore, H can be calculated by using this correlation, okay? Expression that we have here. This exactly this is what version that we have. Therefore, that we can see now the heat transfer coefficient is 4,184. You can see it's very high, okay? That indicates that this is turbulent flow is going out. There's a lot of movement of the fluid passing energy from the surface of the pipe to the fluid, okay? Therefore, now we have the heat transfer coefficient, we have mass flow rate, we know the length of the pipe, we know the diameter of the pipe, mentioned to calculate the exit temperature, right? Remember, we mentioned calculate the exit temperature. Again, we have those equations that we have. Any questions so far, please? You done? Are you done?
Yes, sir.
Good, sir.
I have a question.
Yes, sir.
Why did we not use the Nusselt numbers equation for large temperature difference? Like the one I think you said if there's the difference between temperatures of the surface and the fluid is large.
Here we have some of the correlation that we have. We can use
Yeah,
this,
the one on the bottom.
we can use this one, but this one you need to know a little bit more information about the friction factor, that you can calculate the friction factor from this expression and put it here. This is one option. You can use this option. This is the process of heating. This value of n is equal to 0.4. You can use this correlation right here, the one we use already. Okay.
What about?
Well, let me go to that. When the variation is large, you can use this correlation. You can use it. You can see the number is almost more or less all of them are the same. Look at it, 0.023, 0.027.
But in our case, the real number is larger than 10,000.
Your real number is larger than 10,000. That's right. You can apply this
Yeah.
equation. You can apply this equation. All of them is acceptable, sir. All of them are acceptable. Okay.
Yeah. Okay. Thank you.
No problem, sir. Again, the question here is trying to just make, but this process more, I like this equation because this is making the correction based on the heating process of cooling, but also this one is doing it, okay? Again, the temperature is, the difference is around 140 degrees. That's correct, that can be done here, right here, okay? And also you have this correlation here. The Prandtl number is 0.7, 2 point something, satisfy here. Again, this satisfy this correlation, but that one is much easier to apply. Therefore, we would like trying to look at what is the temperature, leaves the pipe. Again, we have for this a constant heating plate. Therefore, you can use this correlation that we have here, okay? Again, this is only applied for the case that constant temperature, constant surface temperature, okay? You cannot apply it for constant heat flux, okay? You cannot. You have H, you calculate the diameter, this contact area between the fluid and pipe, and this is this one. You have the mass flow rate is given, the information to you, and CP of the water. And therefore, you find the temperature, the water leaving the pipe is 148 degrees. And you can see now 148 plus 20 become 168 divided by 2, become 85. Oh, we were lucky. Okay, therefore this is it. But again, your judgment is always helpful from the beginning. It's not a 1 meter pipe, it's not 10 centimeters, it's 14 meter pipe. Therefore, we have to look at here is long pipe. There is enough time for the heat transfer between the fluid and the pipe. And we look at here and we can calculate how much energy has been transferred. You can use this equation that we mentioned here, or you can use mCp times T in minus T out. Both of them, they should give you the same answer. You can use this correlation. This shows how much is convective heat transfer. Convective heat transfer between the fluid and pipe. And the same thing, this is the same energy that transfers from inlet to outlet. This amount of the energy has been given to the fluid. The temperature goes from 20 to 158. Therefore, if you write Q is equal M CP T out minus T in, and you should get almost the same answer, okay? And at the end, they will asking you how much has been condensation. Therefore, this is the energy we got it from the steam to heat. Therefore, that steam has to condense. Therefore, we can calculate how much energy, what is the mass. The mass is 0.209 kilogram per second. This is the amount of the energy we remove it from the steam. This amount of energy released per kilogram because of the phase change that we have from steam to the liquid. Therefore, this is 0.209 kilogram per second. Any question, please? Any question, please? Ask.
Sir?
Yes, sir.
Why do we have to use HFG?
Because this is the energy that when you transfer a kilogram of steam to kilogram water, you need remove some energy.
That I know. Yes.
That's the value.
Okay.
Okay, because we mentioned condensed. Therefore, the steam come here, hit the pipe, condense to the liquid, and that's at 160 degrees. Okay.
And please, for question, please, sir.
Yes, sir.
For the delta temperature.
This one?
Yes, because we know that the water entering the tube at 20 degrees.
That's correct.
And exit at 148.
That's correct.
So the delta temperature won't be 148 minus 20. That's it.
That's the temperature difference when you write the equation Q is equal mc delta P. When we are using this equation here, this is the temperature difference between the surface of the pipe and the liquid. Okay, let me go back. Let me just go back, make sure that you really catch me. This one, okay, sir. This plate, okay. The temperature come at 20 here, sir, and leaves around 148 here, right? Okay. But the temperature of the plate, the temperature of the pipe, it remain constant. Therefore, the temperature difference between the fluid and the pipe keep changing. At the beginning is this much, at the end is this much.
I got it. Thank you.
Okay. Therefore, we try to find an average. In this case, we call it log mean temperature difference. Okay, that's the one comes here. No problem, sir. Ask, please. Any question comes to your head, to your mind, ask, please. Any question? Therefore, here we calculate it and we find this is the amount of heat. Good. Let's move. Please ask if you have any more further question. But again, when we're trying to calculate the heat transfer for the pipe, when it's turbulent, there is, okay, when it's turbulent, and we will have to go with the pipe. Therefore, we have a set of sort of correlation that they gave you also for that case, okay? Therefore, here just mentioned you have to sometimes, if you have a turbulent flow, but the length of the tube is not 10 diameter, is smaller than that, you have to make some other way of doing it. Therefore, you have some correlation. And the other one is sometimes you have two fluid, one inside the other one. Assume you have one fluid pipe, that fluid going to it, and the other one here is you have sort of another fluid, okay? Another type of heat exchanger. Assume here you're putting one liquid and the other one here liquid. Therefore, in this case, you are trying to calculate the heat transfer between these two, okay? Not here. You already have all information about inside. But how about between these two tubes? Therefore, here again, we are coming up with trying to calculate the hydraulic diameter. Therefore, this is the way you calculate the hydraulic diameter for flow between two pipes here, okay? Again, the same thing you calculate for your heat transfer coefficient, okay? Therefore, to make sure that this is the case that you have, again, here give you dependent ratio of these two diameter. Again, here is Nusselt number, fully developed, my friend. Again, remember, for fully developed laminar flow, when you have any old pipe, okay? This is depend on the ratio of this side, inside diameter to outside. This is the diameter of this pipe here, and this is the diameter of outside pipe here, okay? Therefore, depend on that one, your Nusselt number is changing, okay? Therefore, this you have to calculate. And also sometimes in order to increase the heat transfer coefficient, again, this is general information that we're giving to you. Here is something we have add inside the pipe, because in order to increase the heat transfer, okay, we can something we added to outside, something we added to inside, therefore something we do that, okay? The heat transfer turbulent flow in the tube has been increased by as much as 400% by using fin, okay? Therefore that you can see that if you really would like to do that, sometimes you have to, of course, you have, there's nothing free. Of course, you have to put more pressure drop, but here is, there is a compromise system between what is the approach, which one is more effective. Okay. Any question, ladies and gentlemen? Therefore, hopefully at this moment, I can mention chapter 8 bye-bye. We understand what is the meaning of average velocity, average temperature. It means the velocity inside the tube is not a function of R. The temperature is not a function of R. We also analyzed a case for two scenario, constant heat flux, constant temperature. We have a set of correlation for here, set of correlation for here. We understand the physics of the entrance, because when it's not fully developed, the Nusselt number will be different from here, because we have set of correlation for laminar flow, for turbulent flow. And also we have done something for temperature profile for Nusselt number and so on. We did calculation, and based on that one we have. Therefore, you have some idea. Again, this is not in detail. They gave you only one sample solution to each process. But if you're really dealing with any of these cases, and if you would like to more accurate related to your application, please go to the library and try to find the most appropriate. If you go from one textbook to another textbook, you can see the equation that you have in your textbook. In the other textbook is not there, because each writer selected as one certain temperature. As I mentioned, again, there's very close relationship between roughness, because as we increase the roughness is acting like a fin, and also disturbing also for disturbing the velocity profile. It means make it more turbulence, more mixing. Therefore, there is more heat transfer. That's why some of the correlation that we had, you can see also there is in those equations you have effect of roughness, friction factor F. Okay, and we have some application. Again, we have dealing with pipe. If you look at the duct for air conditioning in the building, you can see all of them are rectangular. Therefore, sometimes we are dealing with non-circular tube. Therefore, we have also a way to calculate an analogy between diameter. We call it hydraulic diameter, and we do calculation of Reynolds number and Nusselt number based on DH, hydraulic diameter, and simply define is 4 area times perimeter. Okay. And we had also some application we show when you have annual tube together here. Again, we have also, we can calculate the way for Nusselt number for interior and exterior, as we have the table that we show you. And we, again, here just only give you some general idea, because you already know what is fin, you know what is heat transfer enhancement, but sometimes again, not only we applying to outside of the pipe, but also we apply inside the pipe. Okay, depend on the application, depend what design we have. Sometimes easier to install if we are dealing with the fluid that we have to pass it through the pipe, we can add it to the pipe. Therefore, this is just an overview of knowledge that you please pay attention when you're reading, read between the line, because the general information is very, very important for your understanding. Okay. Don't only look at the equation, trying to understand why they consider this phenomena here, why they did not consider the phenomena here. Trying to convince yourself, and if you have any question, please do come and ask, okay? Because this is one of the important part of your future career, because you will be involved in design of the system, and wherever you go there, you need to know more about the heat transfer coefficient and how to calculate that part. Okay. Let me see, what time is it now? Unfortunately, we don't have time. Again, remember this equation. Did you solve this equation? This question? Do you remember? It seems you don't remember. Good. Therefore, I will stop here. I will do the next lecture. Do you have any question, ladies and gentlemen? Any question, please? We have 2 minutes, 3 minutes. If you have any question about any chapter, I can give you some hand. Again, for those of you who came late, I request the exam to be done on call, and they're supposed to send you some information. I will check, verify with them, and we're trying to keep you informed that what I ask that you provide the solution. I believe they will give you time that you can upload your solution. Okay, it's not only answer, but they would like also to give you the chance to put you the solution, that in case if you make a mistake in calculation, at least you will not be penalized for the whole question. The question is, again, is very easy. It's not easy, but that means in the level of what we work out during the class, during the tutorial, through the assignment. And if you would like to pass the exam successfully, please, please, please do not memorize. Try to understand, because I have 2 questions, the same question, but there are 2 different solutions, because depend what is given, what is unknown. And again, when you try to solve the problem, the same thing we did in the class, just start logically. Try to understand what the question information is given to you. Try to sort of separate the question from the rest of the material. This is the question, this is the information is given to me, and this is I have to provide. And then try the equation, then try to apply the number. Just don't take randomly the equation, just plug in the number, at the end you will end up that's absolutely wrong, okay? Try to understand the physics of the problem. This it will remain with you for the rest of life, okay? The equation, you will forget it tomorrow. Any question?
Sir?
Yes, sir.
Are we going to solve some extra problems next lecture, or?
If you be a nice guy, yes. But the only time the question will be helpful if you read the chapters and you have a complete understanding. I can send you the problem with the solution. That's the easiest way to do it. But the whole idea of doing it in the class here, we can have some discussion. And we can discuss it, why this solution, why not that solution. That's the way you learn. Yes, I will provide you 1 or 2 questions. I will do it next lecture, but please try to finish until end of chapter 6. I will go chapter 2, 3, 4, 5, 6. Some question that help you to have much better understanding.
Thank you, sir.
Thank you, sir. Anyway, ladies and gentlemen, the lecture is over. Again, my apologies for what I said, because I was told that there are sometimes some people creating problem. I thought that's the one.
So, Professor, you said there was only 2 questions for.
I never said such a thing, sir.
Okay, because I thought you just said there's 2 questions with 2 different.
No, sir. I never said. I said there could be 2 questions. They gave you the same information, but 2 different solutions.
Okay.
I can give you 2 questions exactly the same, but what asking will be different. Okay. My point was, do not memorize anything, sir. You have enough problem right now with solution, trying to understand them, that why this is a solution. Okay. Thank you again. All the best. I'm here. If you have any question, please ask me.
Sir, I have a question from chapter 5. Do you have the textbook beside you?
I have a text, but the one I have is fourth edition. They sent me a copy, but I have not received it so far. What exactly would like to say?
This is the two-dimensional heat transfer question.
Yes.
There's the relation talking about the delta time. It says this is a sample question in the textbook. So it says delta t smaller will equal to L squared divided by 4 alpha multiply 1 plus HL over H.
I do again. Give me at least one idea, because I did just the addition I have is fourth edition. Just tell me which one it is, which problem it is that I try to figure out.
So this one in my book is example 5-7.
5.
Example 5-7.
5-7. Let me see. Okay, this is transient two-dimensional heat conduction in L bar.
This one is a nodal analysis, two-dimensional nodal.
Now I understand. This is the example 5.7, sir.
Yes.
Is it the title is transient two-dimensional heat conduction in L bars?
Yes.
Okay, good. We are the same. Okay. Now, what is the question, sir? Now,
at the end, it's at the end where we have all the formulas set up, all the energy equation set up.
Okay.
Introducing the relation that delta time equal to something.
Okay.
Yeah.
For now, they wrote the equation for all different nodes, and they're trying to use explicit technique, my understanding, and they're trying to find what time step they should take.
Yes.
And based on that one, I can calculate here. They have a different equation, and there is one equation they need to satisfy 1 minus 4 pi minus 4 pi HL over K. This has to be more than 0.
Right.
Based on that one, they put the number and they find the delta t has to be less than 10 seconds. In order this problem converge, the time step they have to take, it has to be less than 10 seconds. And another equation that you calculate, mentioned that t has to be 0.222. This is the Fourier number. Okay. Therefore, this is the calculate and mention that in order to converge, the time step has to be 10 seconds. And they put that 10 second on Fourier equation, and they find the Fourier equation. The Fourier number is 0.222. Okay.
Right.
Okay. Now, what is the question, sir? Did I answer the question?
My question is how to get delta t.
Again, the delta t, if you look at that equation that mentioned, if you look at the equation, for example, for node number 9, on the middle of the page, mentioned time temperature at t plus 1 at node number 9. You see that equation?
Yes, yes.
It has a coefficient, and that coefficient of the temperature node number 9 is 1 minus 4 minus 2 pi, and so on. That coefficient has to be positive in order your set of equation to converge. Therefore, from that one mentioned this term, this coefficient has to be positive, and that mentioned the next step. Mentioned 1 minus 4 Fourier number minus Fourier number. This has to be bigger than 0. It has to be positive.
Okay.
Okay. Therefore, that's the way they calculate. We mentioned in order that this formula technique work, it has to converge, and that's the constraint that you have. In order to converge, the coefficient of that temperature, that node has to be positive. If you're looking for node number 8, the coefficient has to be positive. In this one, they look at this case, temperature at node 9 is critical, therefore they look at that one. If you look at, for example, temperature number 1, temperature number 2, all of them, their coefficient is this. If you look at the previous page, note number 1, look at the coefficient for the temperature number 1 at I. Look at temperature node 2 at time I, and all of them, you can see this coefficient remain there. Therefore, they mentioned this coefficient, it has to be positive. If it's not positive, will not converge. We divert. The temperature goes up and down and goes to plus or minus infinity.
Okay,
And that will dictate what the time step you have to take in order to be sort of converge.
Okay, perfect, sir. I see that the coefficient has to be bigger than 0, but if you look closer, I didn't get how the relation, the Fourier number, transfer to delta t, the relation for delta t.
But a very good question. If you look at here, if you go last line, mention what is the Fourier number it is. If you look at the below, you see the tau Fourier number is equal alpha delta t L square. Therefore, you go back and you place on that equation that you have Fourier number. For tau, you put it that number, alpha delta t L square. And when you simplify, you get that equation that you have at the end.
Okay, okay, perfect. That's it, sir. Thank you.
No problem, sir. Any other question, ladies and gentlemen? How is the tutorial?
Great.
Good. Thank you again. If you may leave, if you have any question, I'm here for the next 5-10 minutes. I can answer any question you may have.
Thank you, sir. Have a good day.
Thank you. You too.